as T sub diff can be defined as, think about diffusion coefficient unit, it's a length square over time. So this must be length square over diffusion coefficient. Let's put this as a equation number 1. Likewise, convection time. Convection time as T sub convec. And that will be distance over velocity. So, okay, so that's distance over velocity. So then what are we interested? We are interested in these two times crossing over or matching together. So when T diffusion equals T convection, then when does that happen? That means, let's say this length as a characteristic length as L star will be defined as D over V. And diffusion coefficient, as we saw it, 10 to the minus n. So I just write down in this way, 10 to the minus n and centimeter square over second. While velocity or local flow velocity, let's just, yeah, we can set up as a, for example, 1 micrometer per second. Just let's assume. Okay. Then let's, to make these, to compare these, like there's a L to the square, so it's power. So it's sometimes easier to consider and compare this in log scale. So let's just take a log of these. So let's take ln of 4, 1, and 2. Then what we will get is ln T diff, diffusion coefficient, with 2 times ln L minus ln diffuser. And like ln T convec will be ln L minus ln V. Let's make everything as a non-dimensional. So how can we draw this? So that as a number 3, number 4. So this will be x-axis as the ln length scale and y-axis as ln t. So then the slope for this convection will be 1. Let's say slope of this is convection. Then what is the slope of diffusion, which is 2. So we will be having a bigger growth of this. Let's write it this way. Okay, so that's diffusion. All right, so what does this mean? There will be the crossing point, and that we can define as ln L star, which is when these two becomes the same. And we can now understand this from here. So that on the right side as a, now thinking about time is a faster means more efficient. So on the right hand side is convection time is smaller. So it's convection dominant region. While this left side is diffusion dominant. So what does this imply? Is depending on the characteristic length. So longer scale, convection will take less time, meaning that convection will be more efficient. On the other hand, it's a smaller scale than L star, then diffusion will take less time or diffusion process will be more efficient. So this gives an insight of how and why our organisms has developed from bacteria to eukaryotic cells and multicellular organism and like primates like us, which develops an efficient circulating system. So let's have an example. Let's For example, for let's say proteins, which has about diffusion coefficient, let's say d sub p is about 10 to the minus 7 centimeter per square, then we can compute this L star, assuming like, let's put the velocity of 1 micron, then what it'll be like 10 to the minus 7 centimeter square per second divide 1 micrometer per second, which turns out to be about 10 micrometer. And okay, so that's good number to consider. What about small molecules or gases? So that's diffusion of, let's say, gases is about 10 to the minus 5th centimeter square per second. Let's go back to check the diffusion coefficient of small molecules in liquid, 10 to the minus 5th. Then let's see, L star, the 10 to the minus 5th centimeter square per second. Let's see, about this is about 100 times longer. Let's put as a length scale of 10 micrometer per second. What will happen over here? So centimeter, 1 centimeter is a 10 millimeter, and 1 millimeter is 10 to the 3rd micrometer. So that's the 10 to the 4th micrometer, about that. So this will be 10 to the minus 5th, 10 to the 4th square micrometer square per second over 10 to the micrometer per second. And this will be 832. So about 100 micrometer per second in this case. So let's see. I just note that this is just a simple approximation, just to try to understand the implication of this. What does that mean? So protein case, this length scale for characteristic length is smaller, that we kind of understand. So what this means is a very small scale, like length scale is a 10 micrometer or even small, a cellular size, then this is kind of characteristic length, or smaller length scale, diffusion will be dominant for that. And this is the crossing point. While let's say gas or small molecules, if we assume that the local flow velocity is 10 micrometer per second, then what comes out is 100 micrometer per second. And that's kind of, the length scale smaller or bigger, and these gases will diffuse more efficiently by diffusion if the length scale is within 100 micrometer. So I hope this one gives you some insight for understanding this phenomenon. Okay, I want to add a little bit on here, because when I look at the table, proteins in liquids can have diffusion coefficient 10 to the minus 7 till 10 to the minus 6, which is 10 times bigger. I want to change velocity as a 10 micrometer per second, and that will have 10 to the minus 6 to this will be about 1 to 10 micrometer. So for proteins to move around, diffusion will be efficient in 1 to 10 micron scale or less. So which means probably inside the cell or bacterium, which has the size of 1 micrometer, diffusion alone will be enough, and we don't need any convection or relevant. While gases and small molecules, the diffusion coefficient, the versus convection, this crossing over happens about 100 micron. Okay, so I think I have a wrong unit here. So about 100 micron. So with smaller than 100 micron, we probably don't need a vessels because diffusion is still efficient enough. So hopefully this gives you a good idea and insight.